All right, so this next section is called the rank theorem. So this is a pretty important theorem. It tells us about the dimensions in our column space as well as the dimensions of our null space. So let's start with the definition of rank so that we know what we're talking about. All right, the rank of a matrix A written as rank A is the dimension of the column space of A. All right, so the rank is something used to describe a matrix, and it's just the dimension of the column space of A. So basically how many linearly independent columns are in A. All right, another definition we're going to need is nullity. The nullity of a matrix A written as nullity of A. All right, let me turn off my notifications here. Okay, so the nullity of the matrix A written as nullity A is the dimension of the null space. Okay, so in summary, whenever you see rank of A, that is just the dimensions of the column space of A. And that's a C. It kind of looks like a parentheses, but it's a C. Which we know is the number of pivot columns. All right, so rank is just a number. How many pivot columns does our matrix have? And then we have nullity of A. Well, that is just the dimension of the null space of A, which is going to be the number of free variables we have. Also, opposite of this, the number of columns without pivots. So as you can see, the rank and nullity are very much related to each other. So the rank is the number of pivot columns, and the nullity is the number of columns without pivots. So when you put them together, you get all of A, like the dimensions of A. All right, so that's basically what our rank theorem says. So let's write that out. So remember, named theorems are important, so you should know what this one says and be able to use it if you need. All right, so the rank theorem says if A is a matrix within columns then we have this equation. The rank of A plus the nullity of A equals N. So rank plus nullity equals the number of columns. Number of pivot columns, number of non-pivot columns equals the total number of columns in our matrix A. And that is the rank theorem. So let's look at an example and use the rank theorem to answer a question. All right, so let's look at a matrix 3 by 4 again. Down my columns, I have 1, -2, 2. And I have 2, -2, 4, 0, 4, 0, and then -1, 5, -2. I'm going to go ahead and row reduce this. Put it in RREF. So I got 1, 0, 0, 0, 1, 0, -8, 4, 0, 7, 3, 0. All right, so we should know how many elements are going to be in our column space. We should also be able to quickly see the basis of our column space. So let's go ahead and check out the basis first. All right, so it's going to be the columns corresponding to the pivots. So it's going to be the first two in this example. And then you can just simply count. How many things are in the basis? There are 2 things. Well, that is the rank of A. Same as the dimensions of the column space, which is the number of linearly independent columns of the column space. And the answer is 2. All right, how many free variables do we have here? So looking here, well, what's left over? So we can figure out what x1 and x2 are, but it looks like x3 and x4 are going to be free variables. So we have 2 free variables. I'm going to say since there are 2 free variables, the dimension of our null space, also known as our nullity, is 2. And so how does the rank theorem come into play? Well, I could have just figured out only one of these and known the answer to the other, right? Because the rank theorem says that 2 plus 2 equals 4, where 4 is the number of columns of A. All right, so that's about all for this section.